Hey everybody. You guys will be shocked to hear that Ellie was the first one to send me some homework questions she'd like me to go over. And they're good questions, so I thought I'd go over them. Alright, starting with number 16 here. How do you use the binomial theorem, as opposed to just distributing it out or using Pascal's triangle, to expand each binomial? Now this is going to be a little bit tedious, and we'll see how far we can get. But the binomial theorem, what that says is if you're starting with a plus b raised to an nth power, okay, you can treat the expansion like a series that always starts at 0, goes out, starts at 0 with an r on the bottom and an n on the top, where n is your counter and n is also the degree of the polynomial that you're talking about, the degree of the binomial, which you're going to raise it to. So then you wind up with each n factorial on the top, r factorial, and n minus r factorial on the bottom. Your a will be raised to a power of n minus your counter, the degree minus the counter, and your b will just be raised to r. One word about this counter, since it starts at 0, if you're interested in the first term, r is 0. If you're interested in the 10th term, r is 9. If you're interested in the 5th term, r is 4. Your counter, when you start counting at 0, is always 1 less than whatever term of the expanded polynomial you're talking about. So how does this apply to d plus 2 to the 7th power? All right, so for the first term, we're just going to plug in. We're going to work out this series here, okay? Plugging in 0 for r for the first term, and in this particular case, n is 7. So the first term is 7 factorial over 0 factorial, which is 1. Remember that bit of weirdness? Over 7 minus 0 factorial, x to the 7 minus 0, x is d in this case, sorry about that, d to the 7 minus 0 power times 2 raised to the 0 power. All of which gets us, well, this is going to get us 7 factorial divided by 7 factorial, so that's 1. D raised to the 7 minus 0 power is just d to the 7th, and 2 to the 0 is 1. So that's our entire first term. Our second term, continuing to plug into our binomial theorem over here, counting from r equals 0 to r equals 1 to get to the second term, is going to be 7 factorial over, r is now 1 factorial, 7 minus 1 factorial down here on the bottom, d to the 7 minus 1 power, and 2 to the first power. So we put this all together, what we're going to get is 7 factorial divided by 6 factorial, which is just 7, times 2, which is 14, and then that's going to be d to the 6th. So that coefficient, this 14, came from working out 7 factorial divided by 6 factorial and multiplying that by 2. Okay? Used a couple Easter eggs in there, but let's see if you can figure them out. Now for my next term, what I would do is, now I'm on the third term, so r is actually 2. Here's the 0 term, here's the first term, well, here's the first term, the second term, and the third term. For the first term, we started counting at 0. So the second term, r is 1. The third term, r is 2. So when r is 2, this is 7 factorial over 2 factorial times 7 minus 2 factorial, d to the 7 minus 2 power times 2 squared. Okay, maybe I'll do a little side work over here. Just looking at this first part of the coefficient. This is where the coefficients come from in Pascal's triangle, by the way. We're going to get 7 factorial over 2 factorial times 5 factorial. So that's 7 times 6 times 5 factorial divided by 2 times 5 factorial. So those go away, and that's going to leave me 42 divided by 2, or 21. But that 21 is going to get multiplied by 2 squared, which is 4. So my actual coefficient on my next term is going to be 84d to the 5th, working out the 7 minus 2 there. So again, this whole coefficient of 84 comes from working out my factorials and then multiplying that by 4, coming from 2 raised to the 2nd power. Okay, I could go on, but I hope you get the idea. This is how you would use the binomial theorem to go term by term and expand the entire thing. Usually that's why we just use this to find the 3rd, 4th, or 5th term, because it's kind of a tedious way to do it. For 7 degrees, I would probably draw the triangle instead, unless the directions specifically say you have to use the binomial theorem to do it. Working out a couple of these like this, however, that is a great way to learn the binomial theorem. All right, let's see what else Ellie had in mind. Find the sum of the first 8 terms of the geometric series. Okay, so this is a geometric series, and it looks like, okay, geometric series in general, they have an explicit rule, sorry, I keep saying that, of a sub 1 times r to the n minus 1. You plug in a number, you plug in 5 for this n, you get the value of the 5th term. Plug in 10, you get the value of the 10th term. They also have a summation formula in general, a finite summation formula where it's the first term times 1 minus r to the n over 1 minus r. And if you're going on forever and adding up an infinite number of them, it just becomes a sub 1, your first term, divided by 1 minus r, only assuming that the absolute value of your common ratio is less than 1. Okay, that's the only reason this works. Only with a geometric ratio with a common ratio less than 1 do you even get an infinite sum that's finite. Otherwise, this series diverges and goes to infinity. But it looks like this applies here. So, we have a sub 1 is 4, and our common ratio looks like it's multiplying by root 2. This turns out to be fairly simple, because this common ratio of root 2 is approximately 1.4, which is bigger than 1. The sum of an infinite number of terms, if that goes on forever, is infinity. This is a divergent series. So all the math we actually had to do was recognize that the common ratio was root 2, and that root 2 is bigger than 1, and then we write infinity or divergent, and we're done. You can see why that one was a good question to ask. A little confusing, but at least the math's not hard. Okay, so now we're back, and we're going to talk about number 24 on this page, which is a limit that Ellie wanted to work out, and I think I see why it might have been confusing. So the first thing I'm going to do is pull out our trick for polynomials, where you see that you have an n cubed top and bottom, and you'd really like them to go away. So we're going to multiply top and bottom by 1 over n cubed. You can always multiply by 1. That's kind of nice. It's basically, or if you want to, just think of it as you're canceling out the n cubed, because there isn't anything else going on. Either way you decide to look at it, what you're actually staring at here when you're done is, oh, almost made my mistake that I don't want to make. Rewrite the limit sign. I have not yet let the dog off the leash. So I get 2 to the n over 3. Okay? Now the letting the dog off the leash is the most important part of a limit. You can't let the dog off the leash too soon. If you let the dog off the leash on this first step, okay, then what you get is infinity over infinity. But after you cross out the n cubes, if you let the dog off the leash, the 2 to the n goes to infinity, the 3 just sits there. I mean, another way to look at that 3 on the bottom, we can take that out and write it on the front. A limit, as I think I mentioned in class, is like a semi-permeable membrane. It'll let some things pass through it and other things it won't. Anything to do with the n cannot pass through it, but the 1/3 can. So in 2 steps, we've gotten rid of the n cubes, we've pulled out the 1/3, and now what we're looking at is not a problem. See, again, if you let the dog off the leash on step 1, it looks like this is headed to infinity over infinity. And that can never be an answer. But if you let the dog off the leash after 2 steps of algebra, you get 1/3 times infinity, or just infinity, which is totally fine. There's nothing wrong with that. You can also say the limit does not exist, but either way, it's totally good. Okay? Now, yeah, again, infinity over infinity, highly problematic. Regular old infinity, not a problem. Okay? Now next, we have this one, where the directions were to write this out in expanded form and find the sum. Now a sigma, well, sigma is also a semi-permeable kind of membrane, so there's nothing wrong with writing the 4 outside here and just looking at this as 3/4 raised to the p power as you go from 0 to infinity. So let's expand that a little bit. Let's plug in some points. Okay. You raise p to the 0, you raise anything to the 0 power, you get 1, multiplied times 4, that's just 4. The next one is going to be 4 times 3/4 to the first power. Okay? The next one is going to be 4 times 3/4 squared. Next one is going to be 4 times 3/4 cubed, etc. Didn't leave myself much room for the plus ... but that's okay for now. So if we just looked at this as a series, it might be a little hard to find the pattern, because we'd be looking at apparently 4 plus 3 plus 9 over 4 plus, let's see, the next one would be 27 over 16 when we were done simplifying. But luckily, they already gave us the rule. In fact, they told us a lot. What we're actually looking at is a geometric series, where what we're doing is we're multiplying by the same thing over and over and over again. Okay? So what I just wrote counts as writing it for expanded form. Obviously, I can't write it all the way out to an infinite number of terms. But I now see that since I'm looking at a geometric series with a common ratio of 3/4, okay, well, the sum of an infinite series is the first term divided by 1 minus the common ratio. Again, I can't stress this enough, as long as that ratio is less than 1. So what this is going to be is 4 over 1 minus the common ratio of 3/4, or 4 divided by 1/4, or 16. Add up all of these infinite terms in a row, and when you're done, when you actually get to infinity, which you really can't, but still, pretend you could, you will simply get the number 16. And that should answer the questions that Ellie sent me. Feel free to email me more, or else, as I said, we'll go over them in class tomorrow.